I'm Mikko Uusitalo from Nokia Bell Labs Finland, and being the overall lead for the project. And I start the presentation. The overview on Hexa-X-II is familiar to many, but just to bring everybody at the same level of knowledge, so going through this quickly. We are the next European level 6G flagship, and we have 44 organizations, Nokia overall leader, Ericsson as technical manager, and a very strong, great consortium. The strengths of the consortium are also visible when looking at how well we are covering different parts of the value chain and how well we are representing different points of view relevant towards understanding the future of 6G and wireless. So on this timeline, in the first phase of Hexa-X, we were creating joint momentum for 6G and forming the structuring, framing, creating the initial vision, understanding initial use cases, what are then the technical initial requirements, and how could we start answering those requirements, building up already first versions of the end-to-end architecture, and then passing the baton to Hexa-X-II at this next stage of systemization. So continuing the earlier work, but raising the important question that what really is part of 6G, and also not only bringing up all kinds of options, but start narrowing down what and when is really relevant and what is most relevant for 6G. And that work we are also doing here today together with presentations from all over the world and strongly from Europe. So on this timeline, Hexa-X-II is ending mid next year. That is the time when the technical specification work is ramping up in 3GPP and taking much of the momentum for driving 6G. 3GPP is active already, ramping up process for looking at the use cases, understanding these needs. And for this, there is a set of things going on from European perspective. Please, if you have not been exposed to that before, so please then contact us or SNS ICE project. The Hexa-X-II, we continue the earlier work, drive that momentum, but as the most relevant new item, there is this 6G blueprint and platform. It's very essential for us to have a wide interaction here, and exactly that we are also doing today, as said. Our structure is shown here. So we have work package 1 working on the 6G values and requirements led by Orange, setting the needs for the technology developed in other parts of the project. Then we have work package 2 led by Nokia on this end-to-end system, bringing then together this joint view and forming the blueprint. Then also the architecture design is tying together aspects of the technical work in the project. This part is led by Ericsson. And then we have the technical enabler parts, work packages 4, 5, and 6. 4 led by TU Dresden and University of Oulu, 5 by IMEC, and 6 by Atos. And then, of course, all of this work is strongly used by the work package 7, impact and dissemination, led by Telecom Italia. We already have been operating for a bit more than 1 year, and from all these areas of our work, all those areas, there is first deliverables that have been shared by our website. So the work started from this use case and requirements, and as a next presentation after me and Patrik, you will hear more in-depth information on this. So we have been updating the use cases done in Hexa-X, and here the sustainability from environmental, social, economic points of view is in a central driver role. We have been analyzing, listing the resulting requirements, and also analyzing the business models and creating various stakeholder maps, as well as then looking at the channel models that we need to understand, looking at the higher sub-terahertz, but also we'll be looking at this 7 to 15 gigahertz. And then it's my pleasure to hand over to Technical Manager Patrik.
So I'll continue presenting the other work packets. So the next aspect is on the end-to-end system, and the latest deliverable is on foundation of overall 6G system design as a preliminary evaluation results. In the deliverable, we looked at how the use cases would map to different functional requirements on the end-to-end system, seeing how it spans from connectivity to latency and security, for instance. We also developed certain enablers for the radio protocol in particular. So a few aspects on data recovery or recovery in carrier aggregation, as well as mobility procedure for UE-initiated handover, and some ideas on moving security down to the MAC layer. There's also a lot of work on the intent-based management, how this should be integrated into end-to-end system. As well as looking at how we can integrate end-to-end security, integrating trusted execution environments, or how to ensure the security and privacy in joint communication and sensing. We also developed an end-to-end blueprint of the 6G system and tried to map how some of these enablers would fit into this end-to-end system. The end-to-end blueprint was released in June, and this is an updated version of it. But we can note that we have the traditional infrastructure layer with the access and connectivity, but also compute. We have the traditional network function layer with the access on the core network, but also these beyond communication services, such as sensing and AI, and more intelligent transport functions. We have the traditional application layer on top, but in between we have a network-centric application layer where we can expose certain functionality network to third-party vendors. And we also have these pervasive functionalities that should be present throughout the network with the AI framework, for instance, or this management orchestration. Next, we have deliverable on the architectural enablers, so some scope on the initial enablers. First, we have some aspects on the AI enablers for data-driven architecture. Look, now we can do machine learning orchestration or the management of this intent-based management of the network. We also have some aspects on network modularization, some ideas on how to streamline different network functions to make sure that we run the network optimized and don't over-provision functionalities. They also work on how to do network migration from 5G to 6G to avoid the many options we had when going to 4G to 5G. There's also work looking at virtualization cloud transformation, so how you can orchestrate if you have multiple clouds in a network, or how you can place the computational needs in the network if you have constrained devices in the network, so move some computations to the edge network. There's also work looking at how the architecture will look with flexible topologies. There's an idea of having a management node that can take over some management functionalities, coordinating to more peripheral devices. Looking at how we can evolve the multi-connectivity options from 5G and previous generations to take the best parts of dual connectivity and carrier aggregation. There's also ideas on this delayed computing to see that if you have relaxed requirements on constrained devices, perhaps it's beneficial to wait with the computing until you are in a better position with the device. We're also looking at how the architecture should look like for the joint communication and sensing and device offloading, where the functionality should look like and how the interfaces should look like. Next, we have the work packet on the radio evolution and innovation, with some enablers on the radio design and the spectrum access. So for the radio design, there are many ideas on, for instance, flexible radio, how we should design the radio interface for optimal performance. but also looking at how we can design the radio to be inclusive, to bridge the digital divide. And here the non-terrestrial network is, of course, an important factor. But also looking at how we can make the radio more sustainable, reduce power consumption, but also ensure the security and trustworthiness of the network. There are also work doing channel modeling and simulations on the coverage, in particular in the high frequencies in sub-terahertz, but also in the new 7 to 15 gigahertz band. We're also looking at what optimal waveforms and modulations should be used in 6G. Of course, looking at the legacy waveforms, looking at how they perform in the sub-terahertz is very important. But also novel modulation schemes, for instance, zero crossing modulation, or looking at different polar constellations. AI will, of course, play a major role. So looking at how we can integrate artificial intelligence in the receiver, transmitter, or joint optimization of the transmitter and receiver. For instance, improving the CSI acquisition using AI. Another aspect is MIMO, multiple input, multiple output, with this distributed MIMO or different alternatives of massive MIMO, but also looking at how this reconfigurable intelligence services can be used to improve MIMO operations. For the spectrum aspects, we are looking at how terrestrial and non-terrestrial networks can coexist on the same frequency band, but also looking at how we can expand this dynamic spectrum sharing from previous generation to the 6G. Now we call it multi-rate spectrum sharing, that we can gradually deploy 6G networks in existing frequency ranges and gradually and dynamically shift the frequency between the 5G and 6G where needed. There's also some ideas on this low latency random access, in particular in the sub-terahertz range. For joint communication sensing, there are many innovations in the radio layer, looking at the architecture, different waveforms, ensuring the privacy and security, and looking at how we can allocate the resources for both sensing and communication. And we have a range of proof of concepts, looking at how we can integrate the AI in their interface, this flexible radio with flexible modulation and TRX design, but also a demo on this joint communication and sensing. Next work packet is on device and infrastructure enabler for this. And the first deliverable was looking at what would be the device classes for 6G and looking at how this scales on both the bit rate, but also on the reliability and latency. The first new device is this so-called energy neutral device, which will be a continuation of the 5G ambient IoT, but even more extreme, so that you don't have any power source or battery in the device, which of course will translate to very low bit rates and very low reliability and long latencies. But for very simple devices, this would be very useful. Of course, there's the legacy MTC devices, and this will continue to be enhanced. So for the 6G MTC devices, this will be a continuation of expansion of the narrowband IoT capabilities, but going both higher and lower in capabilities. Next, we have the very mouthful, reliable, high data rate and bounded latency devices, until we find a better name for that. And this is where you need support, for instance, XR devices, where you need guaranteed bounded latency and quite high bit rates. So it's not the extreme terabit per second, but it's a few, perhaps gigabits per second with bounded latency around 10, 20 milliseconds. Then we have the highly reliable low latency devices. They will have slightly lower bit rates, but much more strict latency requirement and reliability, for instance, in industry applications. And of course, the previous device classes of mobile broadband and the URLLC will continue to be relevant and continue to be developed, but we haven't started looking at these since these are very much 5G use cases at the moment. Yeah, similar proof concepts here. The final work packet is on the intelligent management and orchestration, looking at how we can design the smart network management framework. And one aspect of this is this trustworthy management, where we're looking at an integration fabric to control this, where we're looking at two different options: a service mesh, where most everything is connected with everything, or a message broker, which as a man in the middle controlling all this. We're also looking at this third-party management and trustworthy, how we can expose different aspects of the network to a third-party operator, and how this can be done in a safe way. We're also looking at different orchestration mechanisms for this computing continuum, where you could have compute resources from the core network out to the extreme edge or devices, and how we can make sure that we place the computation in the optimal place. We're also looking at how we can have AI/ML-based control in a trustworthy way, so we can trust that the AI does what it's supposed to do without leaking any information. Another aspect is improving this energy consumption. So we have this programmable flexible network configuration and this network monitoring and telemetry. The first one is about how we can set up the network in a programmable flexible way. This monitoring is how we can operate the network and maintain and optimize it while it's running. We're also looking at how we can control the AI/ML operations in a sustainable way, so we can place the AI computations in the best place in the network. And finally, the automation, how we can automate the operations of the network. So one aspect is multi-cloud management. If you have different operators with different clouds, how can these cooperate with each other and serve the users? How can we integrate the digital twin in the network, so we can do a digital replica of the network and optimize the operations and monitor the operations? We also have this closed loop governance and coordination of multi-closed loops, so how we can do a zero-touch operations of the network and where the functionality is needed and how this should interact in different parts of the network. Finally, I'm going to say something about these system-level proof of concepts we're working on. This will be in 3 stages. So the first stage was delivered in December. The next one will be ready in June. And the last one will be ready somewhere next year. So in the first one, we're looking at how management orchestration and diagnostics could be used in a setting. Next stage, we'll look at more flexible topologies, integrating beyond communication and twinning. And final stage, we'll integrate 6G device components and 6G radio aspects with XR devices and 6G radio interfaces. And in each of these stages, we're looking at the different sustainability aspects, both social, environmental, and economic, where it's possible to see how we can monitor the operations. The first proof of concept is looking at the inventory management, where you have this autonomous robots managing the inventory. So you both have ground robots and drones looking at what's in the inventory. And these can manage their own power consumption and coordinate operations between them. The next stage, we will extend this to have a multi-site operation. You still have the inventory management and you have the mock manufacturing in one site, but then you can trigger moving of the manufacturing to a second site, which will use the resources from the same inventory. And you have the coordination of this manufacturing done from the main site. So thank you all. That was a brief overview of the project. You will hear more in the coming presentations.